Today, we're going to discuss the fundamentals of one-dimensional motion. This may seem like a small, insignificant segment of physics, but actually, it is where the predictive power of physics all begins. From predicting the trajectory of an airplane and the miracle of flight, to the exact timing of a train connecting cities together, or determining the times and distances during a classic family road trip. But they run much deeper than this. Equations of motion are used to predict the motions of the planets around our sun, and even the motion of our sun around the Milky Way. All particles and objects in the universe are in a constant state of motion. And by knowing the equations of motion, you can know exactly where our universe is headed, where the universe came from, and where we all are today. So buckle up and get ready to embark on a journey connecting time and space using 1D motion. This is an adventure you won't want to miss. Let's get started. Hi everyone, this is John and welcome to my channel, drjohn.dev. I have a PhD in physics and have been helping students solve problems in physics for over 15 years. For personal help and appointments, visit my website at drjohn.dev. Make sure to subscribe to my channel and hit that like button. So first off, let's go over some basic terminology and a brief background of one-dimensional motion. One-dimensional motion is a subset of kinematics. What is kinematics? Kinematics is the analysis of the path an object takes when in motion. It does not, however, consider the forces causing that motion to occur. For instance, kinematics can be used to solve how long it takes for an object to hit the ground when falling from a building. But why an object falls down instead of up, or why an object falls with a constant change in speed rather than just a constant speed. These are determined by the underlying forces acting on that object. These underlying forces will be covered extensively in later videos, but for now, just know that after analyzing all the forces acting on an object, then that's when kinematics can be used to determine the full details of an object's motion path. The ideas of modern kinematics were mostly developed in 1638 by Galileo Galilei in his landmark work, Discourses and Mathematical Demonstrations Relating to Two New Sciences. In his work, he experiments with the motion of falling objects, acceleration, and the motion of projectiles. He experimentally observes that the speed of all falling objects increases uniformly and is only proportional to the object's time of flight. Previously, people just assumed Aristotle's principle, which stated that heavier objects fall faster than less heavier objects. Considering Aristotle formed his principle in the 4th century BC, it's really surprising no one noticed this inaccuracy for almost a 2,000-year period. Galileo's work later laid the foundation for Sir Isaac Newton in developing his famous laws of motion, as well as developing the calculus relationships that we have come to know today. More to come on Newton's laws of motion in future videos. So if kinematics is the study of motion, what then is meant by motion in one dimension? Sorry, Super Mario. This simply means the object's motion and change in motion are along a single direction or axis. The objects themselves don't actually have to be one-dimensional. Just the direction of motion must be. Here we go! Okay, glad we cleared that up. So, in some of the examples we'll soon cover, this can include anything from a rocket ship launching into the air, a car moving down the street, or a train moving along a track. More on that later, but for now, let's cover some basics. Let's consider 2 points in space, and label them point A and point B. Now, if you were to travel down a path connecting these 2 points, the length of that path is referred to as the distance, labeled here as d1. If you were to travel an alternative path, let's say along D2, this path length would represent a second distance between points A and B, albeit a longer distance. In fact, if you continue to travel down different paths, such as along D3, D4, and D5, each one of these paths represent a distinct distance between these 2 points. That is to say, the distance between 2 points depends entirely on the length of the path taken. Any 2 points can have an infinite number of unique paths, and hence distances between them. Displacement, on the other hand, is the net distance between 2 points. To find the displacement between A and B, you need to find the net change in horizontal position, labeled as delta x, and the net change in vertical position, labeled as delta y. The displacement is then simply the diagonal connecting the beginning tail of delta x to the ending tip of delta y, or another way, simply the hypotenuse of the resultant triangle formed by delta x and delta y. Loosely speaking, displacement represents the shortest distance between 2 points, but in the strictest sense, displacement is not a distance. Displacement also includes a direction, indicated by an arrow. When a quantity consists of a numerical value, also known as a magnitude, with an associated direction, the quantity is referred to as a vector. To denote displacement as a vector, its symbol, delta r, is bolded in the diagram. We'll cover more about vectors in a future video, but for now, know that the displacement of an object is an example of a vector, and therefore must include both a numerical number as well as a specified direction. Also, unlike distance, the displacement does not depend on the path length, and is a single, unique quantity between 2 points. To help illustrate and highlight the differences between distance and displacement, let's look at an example featuring the Pacific Crest Trail. The Pacific Crest Trail begins near the Mexican-California border, stretches through all of California, Oregon, and Washington, and then ends just past the Canadian border in the north. To find the total distance of the trail, you need to start at the beginning of the trail, and then proceed to measure the entire length of the trail, inch by inch, hiking through mountains, valleys, and deserts, and after months of traveling, assuming you didn't die of dysentery, you would finally determine the total distance to be 2,650 miles. What about the displacement? Is it the same as the distance? To find the displacement, we only need to consider the coordinates of the starting and ending points of the trail. Or, put another way, we simply need to find the net distance traveled vertically and the net distance traveled horizontally. Using the difference in latitude from the starting and ending points, the net vertical distance traveled is 1,135 miles. Then, using the difference in longitude from the starting and ending points, the net horizontal distance traveled is 300 miles. The displacement is then the hypotenuse of this triangle, which, using the Pythagorean theorem, is simply the square root of the sum of the squares of each side. After substituting, this brings the displacement of the PCT to 1,174 miles. Notice the displacement does not equal the distance of the trail, and is significantly smaller than the total distance of the PCT. The displacement also has a defined direction, which is indicated by the arrow. So, if you skip the trail and only wanted to find the displacement, you may end up missing some of the scenic beauty of the PCT, but you'll have much more energy left to enjoy studying physics. So now that we've made the distinction between distance and displacement, we can extend these ideas to the quantities of motion. To make a prediction of where an object is going to be located at a certain time, we not only need to know the distance traveled, but we also need to know how much time it takes the object to travel this distance. The measure of how much an object's distance changes over time is known as the speed, and it is equal to the distance divided by the change in time, or delta t. Also note, since time and distance do not have any directional information, speed is not considered a vector quantity. We refer to non-directional quantities as scalars, and time, distance, and speed are among some examples. Now, if we instead want to know how much an object's displacement is changing over delta t, we can use the analog to speed, which is referred to as the velocity. Velocity is equal to the object's displacement divided by delta t. Notice, since displacement is a vector, velocity is also a vector quantity. The velocity's direction points in the same direction as the displacement vector during the time interval of interest. Because distance and displacement can often be different quantities for the same object, speed and velocity can likewise be different quantities. There is also the concept of instantaneous speed and instantaneous velocity. This means the speed or velocity of an object at a particular moment in time. For instance, a train that travels along its route may make several adjustments to its speed along the way, such as taking time to start up, reach its cruising speed, or intermittently stopping at stations. If you simply divide the train's total distance by the time it takes to complete the route, the speed you calculate wouldn't capture all of this information. In fact, total distance divided by total time would only be the average speed for the journey. Instantaneous speed, on the other hand, is the speed of the train at an exact instant or snapshot in time. How would you mathematically find an instantaneous velocity? Notice, the functional form of velocity, delta r divided by delta t, has the same exact form as the slope of a function f of x. If you remember, the slope of an arbitrary function f of x is defined as f of x2 minus f of x1 divided by the difference of x2 and x1. Or, written another way, delta f of x over delta x. So velocity is essentially the slope of the displacement curve between 2 points in time. Now, we can extend this idea of slope a step further to instantaneous velocity. Remember from calculus, to find the slope of a curve at a particular point, let's say x0, you take the derivative of the function with respect to x, and then evaluate the derivative at the point x0. We can apply the same logic for finding instantaneous velocity. Instead of f of x, let's consider an object's horizontal displacement x as a function of time t. Or, put another way, f of x becomes x of t, and the horizontal axis now becomes simply t. So the green curve now represents how an object moves along the horizontal direction x over time t. Now, at some particular time, let's say t0, we can take the derivative of the object's displacement with respect to time, and then evaluate the resultant derivative at t0. This will give you the object's instantaneous velocity at time t0. You can also find an object's instantaneous speed in the same manner. The final quantity of motion that merits a distinction is acceleration. Acceleration is the rate of change of velocity with respect to time. So any time an object's velocity changes, we describe the motion as acceleration. There is a subtlety here that is worth mentioning. Since velocity is a vector, it consists of both speed and direction. This implies acceleration can occur when an object's direction changes, even if the speed of the object remains constant. This idea is especially apparent when an object moves at a constant speed in a circle around a fixed point. Or consider Earth's orbit around the Sun. When at the 6 o'clock position, Earth's velocity points to the right. But as Earth continues around the Sun, its velocity continues to change direction. Even if the Earth's orbital speed were perfectly constant, Earth would still be accelerating around the Sun due to the continuous change in direction. Let's take a step back and review all of these quantities of motion. It's important to note the subtle differences between the scalar quantities on the left and the vector quantities on the right. Throughout physics, the vector quantities on the right will be the quantities of motion most often used. Why? In physics, you're going to encounter many forces and how they act on objects. And, as you'll soon find out, once you determine the net force acting on an object, you'll then be able to determine that object's acceleration using Newton's second law. And once the acceleration is known, then you can predict the object's future velocity and displacement. We've seen how an object's position, velocity, and acceleration are related mathematically. So let's put these relationships together and see how they look when plotted versus time. The plot of an object's motion versus time is known as a motion graph. Motion graphs are useful for quickly visualizing and understanding how an object's trajectory changes over time. To help illustrate this, let's take a ride on Amtrak's Lakeshore Limited train route. This train route begins at Chicago's Union Station and then proceeds to travel 959 miles over the course of 20 hours 12 minutes with 19 stops until finally arriving at New York City's Penn Station. Now, you may be tempted to simply divide the total distance of 959 miles by the total time, 20 hours and 12 minutes. As we learned before, this would give you an average speed, which for this journey equates to 0.79 miles per minute, or 47.5 miles per hour. But with 19 stops and multiple speed adjustments throughout the trip, this hardly captures the real speed of the train while traveling between these stops. To figure this out, we must do a little digging. The Amtrak's displacement versus time data isn't readily available on Google Maps, but we don't need Google for this. We can figure this out. We can use Amtrak's official train route pamphlet to determine the distance between each station. And then we can use the arrival and departure times posted by Amtrak on their website for the Lakeshore Limited route. Once we know the distance between each station and the time it takes the train to travel between stations, we're in business. Let's begin by plotting the train's displacement over time, delta t. And to simplify things, let's just consider the first 3 steps of the journey. We know at the beginning, on trip step 0, the train is at the Chicago station and hasn't traveled anywhere yet. So we can plot the first point on the origin at 0 minutes and 0 miles. The train then proceeds to travel 84 miles in 89 minutes to SOB, or the station located in South Bend, Indiana. We can plot that point next. The train doesn't stop for long at SOB, and then proceeds to travel 17 miles in 25 minutes to the EKH station in Elkhart, Indiana. But notice, for this plot, we're plotting the displacement from Chicago, so we need to plot the train's EKH arrival time at 114 minutes and at 101 miles, which is the displacement from its starting location in Chicago. Now, let's connect each of these points by a straight line. And since trip step 3 indicates the train stops for 3 minutes at the EKH station, we know the train isn't going anywhere during this time, and we can just draw a flat horizontal line after this station. So, in reviewing this plot, a particular point along the green lines represent the train's current displacement from Chicago at a particular time. The green circular points represent the train stations along the route. Now, how about plotting the train's velocity over the same period? If you remember from before, the velocity is equal to the slope of the displacement curve. And looking at the displacement curve, you can see 3 distinct regions when the slope changes. The first being when the train is en route from Chicago to South Bend, then from South Bend to Elkhart, and finally when the train is stopped at Elkhart. So we can find the slope of each of the 3 regions and plot them on the velocity versus time graph. For each region, the displacement curve is a straight line, and hence, the slope is constant over each region. Plotting the slope over time will simply be a straight horizontal line. But when the train goes from region 1 to region 2, it slows down and its velocity decreases. And then finally, its velocity is reduced to 0 while stopping at the Elkhart train station. Before moving on to the acceleration motion graph, it's important to note a key calculus relationship between velocity and displacement. In this example, we use the displacement curve to find the velocity curve by taking the slope, which from calculus we know as the derivative. If we had instead only been provided with the train's velocity information, we could have just as easily generated the displacement curve. To do this, we could use the inverse relationship between the derivative and integral established by the fundamental theorem of calculus. This boils down to finding the area under the velocity curve, from some starting time to some ending time. For example, say we wanted to find out exactly how far the train traveled 60 minutes into its journey. We could integrate the velocity versus time curve by finding the area under the curve from 0 to 60 minutes. This is simply the area of a rectangle with a width of 60 minutes and a height of 0.94 miles per minute. By multiplying the width and the height together, the resultant displacement evaluates to 56 miles. Finally, let's look at the acceleration versus time curve over this period. Remember, acceleration is equal to the change in velocity over time. This definition is also a slope-type definition, and analogously, acceleration can also be thought of as a slope, but in reference to the velocity curve. So, where is the velocity changing along this route? The velocity along most of the route is not changing, and hence the acceleration is 0. In fact, on this motion graph, it only changes 3 times. Once at the beginning of the trip when departing from Chicago, once at 89 minutes when the train transitions from the South Bend station, and then finally at 114 minutes when the train stops at the Elkhart station. While we know that the train changes velocity between the different legs of the journey, we don't have the data for the time interval delta t for each of these velocity changes. We could take a guess for each one, but for the purposes of this exercise, let's assume each velocity change occurs in 1 second. This isn't realistic, but the analysis still highlights the mathematical relationship between acceleration and velocity. And you may also notice that by making the delta t equal to 1 second, this results in the acceleration having the same numerical value as how the velocity changes in units of miles per hour. If you're not convinced, try working out the dimensional analysis for yourself, and leave me a comment below on what you find. If you need help, refer to my video on dimensional analysis, linked in the description below. So, using this approximation, we can find each of the 3 non-zero accelerations and plot them at the appropriate time they occur. Notice, the units along our horizontal axis are in minutes, but we're assuming these accelerations occur in 1 second. So our plotted accelerations look just like vertical spikes at this time resolution. But if you were to zoom in on the time axis, they each have a width of 1 second. And aside from these 3 changes in velocity, the rest of the acceleration curve is 0. It is also worth noting that the acceleration is positive when the train speeds up, like when the train departs from Chicago. And the acceleration is negative or undergoes a deceleration when the train slows down after the South Bend station. One final note regarding the acceleration. Just as we linked the displacement and velocity together before using calculus, the same derivative relationship holds between acceleration and velocity. And just like before, if you were only given the acceleration curve, you could integrate this curve to generate velocity versus time. So even though the acceleration curve doesn't look like much, it's all the information you need for determining where the train is located during its journey. This pretty much concludes the key concepts you need to make motion graphs. But this train wasn't just stopping at Elkhart. We bought tickets for New York. And we already had all that data collected for the Lakeshore Limited route. So, just out of curiosity, what does the rest of this journey look like in a motion graph? Or, in the words of our dear friend Mario,
let's go!
I think that just about wraps things up. Thanks for watching, and I hope you enjoyed the trip. In the next video, we will pick up where we left off and work through the common equations of kinematics. If you like this video, make sure to hit that like button and subscribe to my channel. And until next time, happy learning.